Start. Okay, welcome everyone. I'm Saket. I'm a faculty member at the Center for Digital Health at IIT Bombay, and I'm going to talk about some AI applications in health analytics. So I guess over the last 4 days, you have had a bunch of concepts which have already been. Sorry, I am actually not well. If PhD degree counts for a doctor, then I'm a doctor, but I'm not a medical doctor. So there's a bunch of Center for Digital Health. Just I can just brief you about what the Center for Digital Health broadly does. The idea behind the Center for Digital Health is to develop techniques, models which are applied in the healthcare space broadly. Our lab website is here, and you'll find links to KCDH. It's called KCDH for short. There. So my area of focus is on this field of biology, which is called genomics, where we try to understand when a disease happens, why does it develop. So, for example, if cancer happens, what molecular changes happen? Can we detect it early? Can we predict if one person will behave better to one particular kind of therapy or not? So these are my broad areas of focus. I started my lab 2 years ago, and when I joined back, I wanted to also understand India from a public health perspective. So we broadly develop AI and statistical models for understanding how uh, diseases happen, both from a molecular level, which is, for example, when you go for a routine blood test, the blood has molecules, we can detect it, we can find out what is going wrong. But we can also apply some of those statistical methods that we develop to find out whether those molecules are coming from a disease state or not into understanding problems in public health. And one such problem that I'm going to talk about today is a very simple problem. It's not even a problem. Is how births happen in India, and can we actually understand what is the pattern that underlies them, especially in the light of climate change and decline in total fertility? How do these two factors will play a role? So the models that I will talk about are actually generally applicable. While I will talk about the conceptions problem, I will leave you with some links where you can actually analyze this and do this analysis on any of your own data sets. For example, one particular area that we have been working on is to understand the factors that affect how malaria spreads in a particular community, or how many cases of malaria will we see given that this is end of July in Maharashtra. So I'll talk about it towards the end, but let me get started. So broadly, I wanted to start with giving you the field of what does data analytics try to do. So just like a doctor uses tests to diagnose a disease, a data analyst tries to use methods to mine information about the data and try to draw inferences as to what is going on inside the data. Can we diagnose the problem? Can we diagnose and can we predict the outcomes? That's the broad level of what a data analyst tries to do. Right? So it's the science of drawing information or insights from raw data. We can inspect, we clean, we transform, and we model the data. The idea behind developing these models in the larger scheme of things is so that if I know how a particular disease, for example, happens, or how a particular uh, phenomena happens, I can predict in the future how it will evolve. That's overall the broad idea of doing modeling. It tries to turn these passive records that we have into active tools. So just to give you some flavor, you must have all have some sort of a file that you would be going with to a doctor anytime you fall sick. If this information can be recorded, and we try to record this for the last 10 years, giving those patterns that we see in your body, can we predict what is going to happen in the next 5 years? That is a predictive problem. And some of the models that I'm going to talk about here today, again, are generally applicable to some of these broad problems. So while your EMRs are passive records because they've been sitting in a particular computer, or EMR stands for electronic medical records, you can convert your file into an electronic version and have it digitized, but they will remain passive. They will sit on a computer. You cannot actually do much with it. But what we can try to do is we can try to model it, like what happened in the last 10 years and what likely will happen in the next 5 years, for example. So there are a few regimes of data analytics, and we will do some of this actually in a hands-on exercise if you are carrying a laptop today. If you're not, I will ask you to sit down next to somebody who's carrying one laptop. So we'll do descriptive, which is what happened. For example, the number of patients that come to a hospital. These are descriptive numbers. We can do diagnostic, because why did it happen? So, for example, why are certain number of patients now higher in coming to my hospital? What is the underlying cause to it? That's diagnostic analytics. We can do predictive. We can now, having looked at the pattern, we can predict what's going to happen. This is July, so our hospital, for example, here will start to see a lot of malaria and dengue cases. So with that is predictive, right? And it depends on the rainfall. So if in July it goes dry, it will not, you'll not see patients because there's no cases of malaria anymore. Can be prescriptive, what we should do. So if we know, for example, this is going to be a rainy month for Mumbai, and this is particularly going to be a rainy week, should I start preparing my beds because I will have malaria patients? Should I start procuring malaria, anti-malaria drugs, because a lot of people will be coming with general malaria related symptom. So the easiest way to sort of think this is, for example, if there are diseases which can be preempted, you can deploy, for example, vaccines. One particular example that I will not talk about today is we see a lot of animal bites and stings that happen also, which have a periodic nature. For example, if I want to have the anti-rabies vaccine already stocked up, I should be able to do a prescriptive analysis that I know a lot of cases of rabies are going to come up, so please stock up your rabies vaccines. So for example, if I take an example of a tea shop and try to understand what is the descriptive part of it, right? So for a tea shop, the descriptive analytics will be, I've sold 500 teas, maybe there are like 400 people who come to the tea shop. So this is just a pure number, like it doesn't much add value to it. I can make it slightly diagnostic. Like I can make it diagnostic by asking that maybe more people visit it during the morning because there is an early morning class. For example, we have a tea shop here in Crescent. You should try the tea there if you have not. It's one of the best teas in the campus. We can do predictive, right? So if the person who's selling tea there, if they look through this pattern multiple times, they could actually predict that if I have an exam season going on, I will have to increase my I should make 20% more tea because people will come for tea more often. I could also do prescriptive, right? So in this case, the prescriptive will be if I want to make more money and if it is exam time, I should keep the shop open because people will come at different times during the exam. That is prescriptive. Okay. So the reason we care about all these different regimes of data analytics is because if we look at data in a longitudinal fashion, and that has a lot of information. So I know you're coming from different backgrounds. I think there are people from trade part, there are people from different cadres overall. But one theme that I wanted to sort of highlight is there is a lot of information that we can squeeze out from data if it is collected over a long period. So I'll just highlight two examples. Both of these examples are taken from health because that's what is going to be our focus today. The first one is the natural history of human diseases. What this paper did was to look at simply what I said earlier, which is electronic medical records for the last 100 years or 50 years, wherever they could, as much as they could go back to. And what they found out, for example, if there are people who have developed a chicken pox at some time in their lifetime, what later on, what impact does it have? And if this data is collected, this is just one such example. For example, if I had a influenza at a certain stage, what in the next cycle, what all can I predict? What is going to happen? And the reason you can do this is because if you collect this longitudinal data, by longitudinal, I mean it's data collected over different years for a longer period. You're actually following a patient for all the 70 years of life or 72 years of life. And you're tabulating everything that happens to that person. Now, if you do this for one person, you cannot do much. But if you do this for 1,000, for 10,000, for 1 lakh, for 10 lakh people, patterns start to emerge out. And this is in general true for any kind of data, right? So if you're working, for example, in trade, if you're working in, for example, in consumption and economics, I'll show you some examples. You can actually find out how the patterns are changing and can we predict based on the previous data what will happen in the next course of our life. The other example comes from a famous study. These studies often keep getting debated, which is the effect of the herpes zoster vaccination on dementia. So this is taken from, I think this is an example from the Nordic countries where they had at some point made an age cutoff that if you are above a certain age, you're not going to get a particular vaccine. This is a herpes zoster vaccine. This is for herpes virus, which a lot of us at some point will get infected with. The idea here was that we have very limited stock, so let's try to save the younger population. What they also noticed, again, they did a longitudinal study. They could follow on what was happening to these people. What they noticed was people who had actually not gotten that vaccination were at higher risk of developing dementia. So these insights, while somebody, when they prescribed that the vaccine should be given to the younger population, would not have thought about the implications of it. But just because somebody did their bookkeeping and followed the patients for a longer longitudinal as in a longitudinal study, they could generate these insights. That's a good question. So in this case, most of the time it is an association that gets standoff. That usually people will end up with, right? So there is a very high association that, but there are, because they allow for control for all the covariates that would go wrong, right? So whether people who had higher exposure to these viruses or lower exposure, age, sex, everything is controlled for. So while your question is very spot on, like all of this will remain in some sense associative. The kind of example that we're going to do today also will be what's called associative analysis. Like I cannot say it's causal. I cannot assign a causation to it. There is some statistical methods, however, that we can use to rule out that any other covariate would likely have had an effect. But an ideal experiment to show this would be to go in the lab and take a mouse and give it the vaccine and see whether there are mouse models where you can actually have dementia or not dementia, and see whether that mouse ends up getting dementia. Because you cannot, of course, do this on a human being, because it will take 70 years for that experiment to finish. Okay, so we'll just start with a quick intro to data visualization. I'm sure you've seen some of this already in the data visualization lecture that was taken. But I'll just quickly cover it. So the first thing that I want to cover is this called box plot. So if you have different categories of data and you want to see how is the spread of this data, is it very tight? Is it the same value? You visualize this using what's called a box plot. The name comes because this is a box, and you're plotting different categories. For example, in this case, I'm plotting the length of the sepal of 3 different kinds of plants. What does this plot show you? So this line that you see here is the median, and this is called a whisker. This is essentially a measure of the spread of the data. So this part from here to here is 1.5 times what's called the interquartile range. I will explain this in just a bit. But broadly, intuitively, if you want to understand, it says that if I take this particular category of plants, this is its median sepal length, but there is a lot of spread, which means that some plants will have this length, some plants will have this length, but if I see on an average, most of them have a length of 5, and similarly for the other species. You see one more point here that is an outlier, which says that most of my data point is here, but this is very, very far away from the median. So this is an outlier. So these kind of diagnostic plots are useful to understand that if I'm looking at a particular value which I have measured, is it something which is very tight? So ideally, in an ideal case, if you want, for example, to measure that if I give vaccination, is there antibody response or not, and if you want to test that the vaccine is really working, then you want this particular box plot to be very, very tight, just to say that all people develop similar response to the vaccine that is given to them. It is also possible that if the vaccine is not really working on a lot of people, then you'll start to see a lot of spread here, which is some people will get a lot of data, but some people will not elicit any response, in which case you can actually measure and quantify that that particular vaccine is not working. That's correct. Yes, that's very right. Right. So this essential contains a lot of your information. So this is this is the first quantile of the data. This is the third quantile of the data, and this is the second quantile of data. So you have 50% of the data is largely going to follow in this box. Right. So this is measuring. So there is, I will explain this in just a bit. So let me use the board to explain. So in often cases, what we see is our natural distributions our natural distributions usually follow what's called a bell curve, right? So you might have probably heard of this name. This is a bell curve in the sense that it looks like a bell. It's also called, this is either called a bell curve or a normal distribution or a Gaussian distribution. These are the same name for everything. So for example, if I measure the height in this room, this will be the mean. So let's say the mean will be like 5 feet, and this is the measure of the spread. On what I'm plotting on the y-axis, on this axis, so this is x-axis, here I'm plotting the height, and here I'm plotting what's called density. You can think of this as frequency. So what this essentially implies is most people in this room will have a height of 5 feet, but we know that everyone is going to have a different height. So this is a spread. So maybe this can go up to, let's say, I think nobody will be 3 feet, but 4.8 feet and maybe 5.2 feet, right? I think I'm doing underestimation of the height, but that's one possibility of what could happen. What this essentially says is most people, so let's say there are 5 people who will have this height, but then every other height, lesser people have it. Now, when you look at the box plot, you can see that major mass of information is going to be here, right? Where I can draw the boundaries wherever I want. So this box essentially captures 50% of the data. So this is going to capture 50% of the values that you see here. And that is what this captures. But there is also going to be some spread because there are people here as well, which is what this particular thing tries to capture, which is towards the end. So this is called the whiskers of the box plot. This is called whiskers. So in this boundary here, I captured 50% of the data, right? Now there is some other amount of data which is also still remaining. This quantifies how much of that data is remaining. So this is your first quartile. Is the concept of quartile clear? Right? This is your second quartile. This is your third quartile. And your interquartile range is Q3 minus Q1. Right? This is your interquartile range. This essentially is 1.5 times the interquartile range. No, it will depend on how much spread you have, right? It is going to depend on. That's correct. So because as I said, this is Q1, this is Q3. This is not, the symmetricity is not guaranteed. Your quartile, your second quartile can be very skewed towards the first quartile, right? But it's a good point. It will become clear in just a bit. It's a very, very good point that you don't see symmetricity here because I cannot actually visualize while it is summarizing all my information. It is not telling me that are most points here or are most points here or are most points here. It could be anywhere because it's a static number, right? That becomes clear using what's called a violin plot because it looks like a violin. So for example, in this case, you see a very fat belly here because most of the points are indeed close to the second quartile. Right? Whereas in this case, you can see what's happening. You can see that it's a very very thin version. So some of the information is actually skewed in this side. And that's why your second quartile is more shifted towards the bottom. So when you visualize this, it is hiding the information that are most values around here or are they spread? How are they spread? That spread is something which is hidden. So these are called violin plots, but a violin by just itself will not, it's not fully interpretable. You can draw a box plot inside a violin, and now you can see what is essentially happening, right? So you can see that in this case, the reason this is closer to this boundary is because your belly is slightly protruding towards the bottom, which means most of your data points, the density of the data points is higher here. And that's why your second quartile is closer is much below as compared to your third quartile, or it's not symmetric. Okay. Okay. Yeah, please, if you have any questions or anything not clear, please, feel free to stop. You can can also draw a different version of this, which is called a ridge line plot. It is essentially again something very similar to a violin plot, except that now it shows you the median and you've flipped your x and y axis. So these are your different categories. This kind of shows the entire distribution, which is, for example, what the violin plot also was showing. This is kind of like a violin plot. It's slightly easier to interpret sometimes if you want to, for example, see a natural progression. So the moment I see this from here, I can see that this mean is the smallest, followed by this median, followed by this median. And this tells me what is the spread of the data. For example, it can see very clearly that there are some points which have very high length here because their density, which is essentially a measure of frequency, goes up onto the right. That's correct. So Setosa has a on an average, Setosa's sepal length are the smallest. This one is the largest, but still there is a lot of variation within them. So for example, if I take a point from here, it is almost equivalent to like a Setosa. Right? It falls within the regime of Setosa. So there is variation. So that's why what is very important to every time visualize is, especially when you're working with any number, is to look at what is its distribution, how much is it spread. So I think Professor Usha, has she covered hypothesis testing? She might have covered about the spread and everything, right? So the reason the spread is important is because if something is very much spread apart, you can start to see that things can overlap just by chance, right? In this case, for example, if I pick a value here, I cannot confidently tell whether it came from this or it came from this. It could have come from anywhere. Even though this is different from its median, but doesn't tell me that this point cannot originate from versicolor. So that's something which is very important to. Sorry, say that. The B swarm plot, right? So here we are showing density, which is I'm quantifying that I can convert everything to a density scale. So if I calculate the area of this, all of it will be 1. So this entire area for all of these curves, the shaded one will be 1. But it is inherently hiding the total number of points. It is possible that this could have come from measuring 1,000 varieties of Virginica plants. This could have come from just 10, which means that I would ideally, give it more importance because there are more observations. If I want to see these observations, I can draw each observation like a dot. Each dot is one value. Yeah, each dot is one value. And what I've done is I've jittered it. So exactly, scatter plot in 2 dimensions in the sense that I have also captured the density. So for example, all these points here, they have exactly the same value, but I have spread it because there are so many of them which have exactly the same value. So if I plot it, they will all start to overlap on each other, which will not tell me what is the density. This tries to capture the density, which is very much like a violin plot. And again, you can draw the violin above it. So now you have the entire density, you know what is the median, and you also know how many points are making up that particular observation. Okay? Any questions? You can mix and match you can overlay things on each other to just bring in more insights. Okay, so this is what I talked about there, which is what does an actual box plot visualize? So this is your interquartile range, Q3 minus Q1. This is Q2. This point is Q3 plus 1.5 times interquartile range, which is again Q3 minus Q1. This is essentially, if I project this, is measures. So it essentially is a measure of how much amount of information or data I'm capturing. So for example, these 2 boxes capture 50% of the data. The remaining 24.65 and 24.65 is what is captured in these whiskers, which is again the 1.5 times the interquartile range. The reason this is done is as follows. Whenever you see a bell curve like this, a general rule of thumb is, so if for example, if I ever draw that the mean is 0 of a normal distribution, by the properties of what's called a standard normal. A standard normal is something when I said that this is a measure of your spread, or in other words, variance. If the variance The variance concept of variance is captured, is being covered, right? What is variance? So very simply, variance is a measure of, if I take the mean, how different is each observation from the mean squared and summed up. This is the symbol for summing up, divided by the total number of observations, minus 1 and so on, but broadly total number of observations. So if I look at this spread, usually most of the information here, if this spread, which is variance, is equal to 1, will be captured between minus 3 and 3. That's like a rule of thumb. If the variance of the bell curve is 1, most of the information will be captured, 100% of the data will be captured between minus 3 and 3, which is kind of what you can see here. Once it goes beyond minus 3, you don't see much frequency here, which is almost tending to 0. So here we are capturing, and then this 50% plus 24.65% multiplied by 2, which is most of your data essentially that you captured. Okay, so anything that does not lie here will be called an outlier because it is coming from this particular tail where the probability or the frequency of observing it is very, very small. Okay. Okay, so we'll now switch to visualizing doing data analytics for live births in India. So I looked at this problem 1.5 years ago when I was just happening to visualize data coming from the Health Management Information Systems HMIS portal, which is from MOHFW. It puts out data in public domain. Sorry, my slides were hung. So every year we have around 25 million births or 25 million babies are born in India. This is the source of this data is the civil registration system, and you can see that it's still kind of the number of female births is smaller as compared to number of male births. At this point, this is just a descriptive way of describing my data that 25 million births are happening, 13 million male child, 12 million female child. Right? So what is so interesting about it? Like, why should I care? If I now look at number of these people who are born at their house, which is home births. So for example, when I was born, and I think what might be true for a lot of people here, we were all born at home at, mostly hospital births were very, very not very common. Now most of these births, which till 2008 there were 30% births that were still happening at home, that number is subpar 1% now. Only 1% or less births overall happen in India. If we look at public versus private divide, again, this is all descriptive statistics. I'm just looking at the data and I'm describing what I see. So the first slide that I showed you came from the civil registration system, which tallies the yearly births that happen. It doesn't do this at the monthly level. The second plot that I showed you came from the HMIS portal. The HMIS is basically a portal where different health facilities, both public and private, will put down how many babies are being born, how many of them survived, are there some low birth weight babies, what was vaccination given, and all those numbers. That information is collected at the monthly level. So for each month, I know how many number of babies are born. It also tabulates whether they were born at home or in facility. This is what I'm showing you here. Right? So if you look at the public versus private, most of the births still happen in the public facilities, and the private is soon going to catch up. Right? There's a lot of births that are going to happen now. Almost half of public births happen in the private facilities, and this number is growing as we progress. One thing that caught my eye, and I'm going to ask you, is if you look at this pattern. So on the x-axis, I'm plotting the month and the year. So it starts from Jan 2009 and it goes to December 2009. Here it starts from Jan 2010 and goes to December 2010. You can see that it goes up, goes down, goes up, down. Similarly, goes up, down, up, down. And if I see this across different years, this pattern just keeps repeating itself. So now we have done descriptive analytics. Now we'll do diagnostics. why do you think we see a pattern like this? So I'll just flash the slide about descriptive um, analytics once more. So we did descriptive analytics. We described what happened. We have to do diagnostics. Why did it happen? Okay. Okay, that's a very good hypothesis, right? So um, what we see, for example, here is in January there is some births. It peaks in kind of March, drops down to very low values in April, again rises up to August, September, October-ish, right? So if I were to take a poll in this room, I'm going to take a bet. If you have children, it's very likely, if I plot that kind of curve of frequency, you will very likely see a peak in August, September, and October, which is what you see on this curve here as well. So if you try to do diagnostics now, it's a one number hypothesis that it's the marriage season that could be happening. So if I now look at this plot, you're also thinking the same? Yes. So in that slide, I think the India, I saw that slide. I think the India version is not correct. Okay, we'll see. We'll see that. I have to write to him to ask. The foreign one was correct. The US one is correct. I think the India version, which was shown, maybe it was representative. At least in my data, I don't think it is correct. This is the real data. This is what is being measured. So on this is the heat map that you've already seen. So you know how to visualize this. On the y-axis, I'm plotting the month, and on the x-axis, I'm plotting the different years. Each value of the cell is the percentage of births that happen in that month, in that year. In other words, if I take all these values along the column and I sum it, it will all sum up to 100. Yes. Okay. Perfect. Very good. Perfect. This is exactly like a data analyst talking. Yeah. Perfect answer, right? Like births doesn't tell you much because like these are births, so they can happen. They must have been conceived 9 months ago, assuming all of these is natural birth, and they have all the 9 weeks. Right. So everybody thinks that, right? Perfect. Like this is perfect class. Like now I'm doing exactly what you said, which is to look at the conceptions. So if I now look at conceptions, again by reversing or subtracting 9 months from the month of conception, sorry, birth, I see that most are happening in November and December, and then followed by Jan and Feb. Right? So marriage happens here. There's a marriage season. There is honeymoon happening and so on. Right? Okay. Very good. Right? Perfect. However, I'm going to say that there are other possibilities. As a data analyst, while one option is to go with our previous knowledge, as a data analyst, our first job is to test it systemically, whether this is correct or not. So while it is correct that marriages do happen, all of us have been to November weddings and December weddings. People come back from the US and other countries in November, December just to get married. There has to be something there, of course. So if I have a hunch, my job as a data analyst is to not make anecdotal arguments, which is that I know that like a lot of weddings I've been to is in November, December, but to actually go back and test it. That does it actually help me explain, right? Perfect, right? In principle, yes. So far, it's very hard to get hang of marriage data, registration data. But in principle, that is exactly. Hmm. Oh, really? Okay. Huh. Right. Right. Perfect. Right. So in an ideal case, exactly that is exactly what you will do. But I'm a poor man. Like I'm just sitting in my office where it's very hard for me to like make requests for data. So I said like, okay, let's test what all can possibilities exist. Right. So let's try to do diagnostics as to what is happening. Okay, so I when I started, I thought of like what could be driving this, right? So a lot of India still lives in rural India. Like we still follow, a lot of majority of still well, fortunately or unfortunately, is agrarian economy, and a lot of us do reside in villages, for example. So a lot of it could be driven by. Sure, please, yeah. Hmm, 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 hmm. Hmm. Correct, correct. Perfect, right? So we have some hunch. 50%, exactly, right? So it might explain something, but we cannot rely on this. Perfect, perfect, wonderful, right? So I don't have to talk about the next slides, but I will do it still. It is also possible. This is a bit of crazy, right? Like it's a bit out of bounds. Like, maybe new new marriages are happening. During those months there is shortage of contraceptives, for example, and like that's why like a lot of babies are being born unplanned. This can happen, right? It's one of the possibilities. It could be cultural practices. In a lot of cultures, when uh, people don't stay together in certain months, especially if you're a newlywed couple, there are like some abstaining period where you actually don't stay together and so on. It could be weather conditions. Okay, it could be. It's my crazy hypothesis. We'll see whether this is true or not. Okay, but all of the anything that I'm missing here, or do you agree with this? That as a data analyst, as a totally unbiased person, you would want to test all of this overall, right? Could be festival season, which I'm broadly capturing in cultural practices, and see if perfect. You will do all that. We'll talk about COVID also. What happened during COVID in just few seconds. Okay, so if we look at the yeah, any questions? Okay, so if you look at the harvesting cycle or the agricultural cycle in India, we have this Rabi harvest and we have this Kharif harvest. This is just a representative plot that this is the months in which their activity related to Rabi or Kharif, um, and then there is one contribution of Zaid also. They peak. So September, October, November, they are peaking. So maybe once November ends, people go back to from their fields and have time to sort of be with their partner and so on. So it might explain the limited activity here, right? So there is no activity happening in Jan and Feb, and if you recall, we showed that Jan and Feb has higher conceptions. Maybe it does explain. Maybe it can explain some of it, but it doesn't really explain the peaks that we see otherwise. It doesn't really explain what's happening. There is a peak in November as well, right? So it doesn't really explain it. If I now break my data down as what you said, which is part of it is rural but a lot of it is urban, I can break this same heat map that I showed you, which was everything combined into rural and urban boundaries. And what you will notice here is, as you mentioned, COVID. So there is COVID, and I will ask you to explain what is going on here in just a bit. But broadly, what you can focus on is, again, this part is broadly green, this part is broadly red, which means that even in rural, urban, or both of them combined, you have same seasonality. Same seasonality. Okay. Any guesses as to what? It's largely ruled out, right? Because why would it happen in urban? Like, I don't know of a lot of people doing urban farming. Like a lot of us are not doing urban farming. Exactly, no farming at all. Well, in Mumbai, there are areas where you do, because Mumbai is not. It's just a very small fraction, right? But you can see what happened during COVID also, right? So in COVID also, you don't see, if you look at the total burden, nothing changes. So the reason I used to highlight this plot is because the interpretation of this plot is very crucial. So if somebody fudges numbers, right? If the total numbers are fudged, and you can see where that is happening, because what I see in the rural areas, suddenly during COVID, there are a lot of births happening. But in urban, at the same time, when I look at it, the number of births have declined. Now, there is no chance this could happen, because if I look at the total births, if I go back to even the COVID years, there's not much drop overall in what happened, right? Like there's still births happening. There is some drop here, but it seems it's more attributable to data quality. right? So it's more because somebody has to enter whether babies are being born or not. It's not like it gets collected automatically. So essentially what is happening here, it seems, is when they started to enter the numbers, Jan, Feb, March was a busy time for everyone because the world was adapting to this. Maybe there was not a lot of reporting happening and people went back and tried to fill in the numbers. So they got the total numbers right, but the urban and the rural split is, to me, it seems like those numbers are not correct. While the total seems to add up to the right value, there is huge number of births that are happening in the rural areas as compared to the urban areas. Okay, let's try to see if we can rule out anything else. We'll try to say that again. Sorry. Yes. So the reason it got inflated is because this entire column sums up to 100. So if somebody writes down a lot of numbers and gives a lot of value to Jan, Feb, and March, they will start having higher content because all of this has to sum up to 100. So just because this was, I think, entered in retrospectively, these numbers were inflated in the rural areas, and because of this, every other number seems lower. Data entry was the issue. Right. March. But at this point, these reports they're already lagging by 2-3 months. That's that's fair. That's fair, right? Like drawdown effect will come in at 21. That's fair. That's fair. That's fair. Yeah, it seems okay only actually, right? It doesn't seem the data entry could not happen because of exactly because they were also engaged in all these things, right? So it's the same set of nurses and doctors who are doing data entry operations. So they are engaged in other things, but once April or whatever the other first wave came, the mandate was to maybe release the data, and this is what happened. So I think what yeah, so I think what happened was the data was not being released. So it was released later on. That's right. No, so this change is what I'm saying is reflective of data quality issues, not actual issues, right? So on the ground, whatever changes you will see is what he said, right? So if COVID is 2020, you will start to see changes in 2021 in terms of the conceptions. But this is a quality issue, not like a data entry, not a systemic issue of. No, because we started to sort of go back on our everything started to return back to normal. Okay. So let me show you more data and then it'll become clear. And we can leave out also this year because these years were anyway tricky for the rest of the world as well. Okay, so we look at the contraceptive pills which are distributed. So we have been distributing a lot of contraceptive pills. This number actually has been increasing. So that's all good news. That will not explain any seasonality, for example. Though you can see that once it's time for data entry in June, for some reason, the number of pills that are being given out usually start to spike out, right? There must be some reason for that as well. Okay, we can look at, yes, yes. Mm-hmm. Mm-hmm. Involved, exactly, right? So there must be some campaigns. Right. So that could explain it basically, right? We could also look at the at condoms being distributed, and those numbers are actually going down, right? So while the pills are being given more, the condoms, this is all public distribution, right? So those numbers are overall going down. Again, you can see there are it doesn't capture private sale. Yeah, it doesn't capture private sale. Okay. So none of these will hold, which is anyway you had said that doesn't make sense. Conceptions doesn't make sense. However, I would want you to again look at the patterns. So in June, July is when a lot of contraceptive pills start to be given out, and the same pattern you see of condoms as well. But you can clearly see it doesn't explain why I should have more conceptions in November, December, and Jan, Feb. Okay. Okay, let's come to the elephant in the room, which is cultural practices, which includes um, the famous wedding seasons, which is November to Feb. So if I now look at the wedding season hypothesis, is wedding season driving it? Now this is slightly on the shaky grounds. As I said, I don't have access to the marriage registration data, which ideally would be the best thing to have access to. However, I think most of you probably would be familiar with National Family Health Survey. These are large scale family health surveys. NFHS 5, this is based on NFHS 5, where there are certain households which are sampled, people visited, asked questions about when did you get married, when was the first time you started to live together, when was your child born, and all those kind of questions, right? What we have access to is the cohabitation data. What was the first month that you started to live together, right? So this partially captures the cultural practices because, again, I have to make some assumptions there. There's no marriage rate captured. What is captured is when did you start to live together. So if I look at the distribution of when do people usually answer, that answer seems to be May. So if we go and look at the survey, people don't, at least based on the survey data, and so far I've not been able to find any other source which tells me that November is the most month where weddings happen the most. Maybe it is correct because anecdotally we know it's correct. But when I go to the survey data and I look at it, it seems to be May where people are cohabiting together. And you can see this pattern actually repeat across states, right? So again, different states might have different cultural practices, but if you see Maharashtra, Uttar Pradesh, Rajasthan, Karnataka, some of these states is what you're going to do your analysis also on. The cohabitation date seems to be May. So somehow, I have a doubt then that if cohabitation is not happening, at least I don't see it in the survey, maybe it's possible that doesn't explain it. So the only other elephant left in the room is weather conditions. So here what I do is we break this down based on temperature on the x-axis and the percentage of conceptions that happen per month on the y-axis. This is winter months, this is autumn months, this is summer months, this is monsoon. And each point is 1 year of that month, right? So you can clearly see that hopefully you've covered linear regression. I think Professor Mani Bhushan covered linear regression. This is a linear regression line. You can see that it's negatively correlated. Higher temperature, lower conceptions, right? And that happens throughout seasons. And basically in monsoons, there are no conceptions. Very, very less conceptions if you cover everything into account. Okay? So now what we're going to do is I'm going to walk you through how to actually make this more robust, right? So my hypothesis is it's sticky weather, there is monsoon, it's extremely humid or there is precipitation, a lot of temperature conditions, and two people don't want to come together. That's possible. That can happen, that either because of biological reasons, that even if for a baby to be conceived, the sperm and the egg have to come together, but there has to be right temperature conditions for it to be conceived. Maybe, please, yes. Yes. That's correct. Yes. 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 In a lot of practices, people don't want to, yes, they abstain from a lot of practices. That's right. That's correct. That could explain. Correct. Wait. That's what. So a lot of people, separation, a lot of people, especially in the South, I think they're told not to, in the North as well. That's right. Okay. I see. I see. I see. Right. So that could explain. So again, that could explain the July. Hmm. Go back. We could go back, right? We could explain. That's correct. In June, that's a very short duration when a lot of people get married. That's correct. But if that hypothesis was correct, then you should start to see more conceptions that time. Yeah. Let me show that thing. Yeah, let me show that thing. Right. So you see some peak up happening in June, right? So it could very well be, right? I'm not defying that. There's no way for me to prove that that's not happening. But can we do slightly better, right? Let's try to do slightly better and see if there is some relation to this, right? So you will see some version of this plot in the hands-on exercise that we are going to do now. But if I break this data based on different states, starting from Manipur, they are arranged based on the value of the correlation coefficient. Correlation coefficient was captured, right? Has been taught. So this is negative, minus 0.91, and then it's almost zero here in case of Jammu and Kashmir. What this shows is higher the temperature, lower is the conceptions. And you can argue of different things, and it's very valid points. All the points so far have been very valid. But let's just focus on Kerala, right? Kerala, extremely tropical conditions. The variation of temperature is between 24 to 26, doesn't vary a lot. You still see a very tight slope, which means that even in a tropical condition, right? Say that again. It's again, it's slightly variation, but you don't see much. Ah, that's good question. It could be we could actually start to look into why does it happen. I don't have answers for a lot of these places. So I'm cherry picking and I'm telling you some places which are interesting. One of them being Kerala, for example, right, or Bihar, for example, where I come from. Like they are negatively correlated overall. We don't see much happening in Chhattisgarh, and again you can argue why, and I don't know. Don't see much relationship in Chhattisgarh or Jammu Kashmir. Meghalaya also, almost 0.21. It's not very high. But at least even if you focus on the first few states, it's very tight, right? It's very tight. And maybe season explains it, but whether that is the case with Kerala, I don't know, because I don't know the same practices that are followed in Kerala or not, right? And you can break this down based on uh, sort of what is the composition of that state or that district, and we can start to study that together. So that's what we are going to do with this notebook. So if you go to your, I think you have access to this drive, right? DOPT2. This drive, do you have access to? No. Oh, so how are the notebooks shared? Oh, the slides have also not been shared. Oh, that's strange. Okay, so what I'm going to do, okay, so I have a solution for that. One second. So So I will put a QR so that you can access at least my slides, because I don't know why that's not been shared, and you can access the notebook that I'm going to talk about right now. Sorry, I should just call it something else. Oh, okay, so if you click on this, on the left one, it will give you the notebook that I'm going to work with. So you can click on your, for example, mobile, and if you open your WhatsApp or send it to somebody, so that, do you have a group, WhatsApp group? Yeah. Okay, so if somebody can share it there, that will also be useful. I have a URL. It's slightly long. So what I'm going to do is, I am not on the WhatsApp group. I don't know. So there's lack of coordination there. But let me see. URL shortener. Let me shorten it so that you can share it here. Okay, so the URL, it's a bit of a mouthful, but it's this one, short url.at A1 capital N H7, short url.at slash A1 capital N small h7. And I will do the same thing for my slides. You did? Okay, great, wonderful, thank you. Do that for this as well. Okay, these are for my slides. Sorry. And I'll do the same thing for my slides as well. Oh, sorry. Okay, so the one on the right, let me paste it on a different. Yeah, this one are my slides, so everything will be there, so you have access to both of them. This is for slides. So again, if you are able to scan it and if you can share it on the group, that'll be great. Okay, everyone has the link. So you should be able to run this on your own. Like that's how what the idea was. Um, so what we will do first is, I think there has been one exercise on Python, right? Like where you have run either linear regression or something similar, right? Okay. That is a prompt, is it? Yeah. Okay. This also can be done through prompt actually. So for example, what I could do is I could, this is for example my data file, right? This is, it's there in the notebook. I'm just copying it. For example, I could go to ChatGPT, which I don't use, but can hopefully use it. So I can ask, give me the code to visualize this data in a time series fashion. So in principle, this is very useful because I will just going to say if what happens um, if I copy it and let's try to see if I can run it. So all I asked it is, this is my data, help me visualize it, and it will do some errors and so on. So what I'm going to do is copy this. It is on Google Colab, that's right. It's on Google Colab. The code is already written, but I'm just showing you that you in principle there is already a lot of code written. But if I wanted to do, I could um, I could try to do this using AI. It'll do some errors. So right now I will not debug this. But if you have access to these models, in principle you could do the same thing by prompting one at a time. But I will just walk you over what I'm doing. So I have prepared the monthly birth data. This is the file. This is a CSV file. I'll show you what each of this data looks like. I have another place where I've calculated, from IMD, I have the temperatures for each state. And finally, I have the civil registration system data where for total births, and then I have state population. What is the population of each state at each year level? So the first step that I'm going to do is I will run this setup so that all things are loaded. I will run this. I'm going to run this, which is what is going to load my data. And then I will, this is what my data frame looks like. So let me increase the font a bit. So here I have data which is all India and different states. What is year, what is a month, how many males are born, how many females are born, and how many, if you total them, what is the overall live births. Right. So the first thing that we do in this function, I try to just literally put it together and perform analysis, where a time series analysis. Before I do a time series analysis, what I'm calculating is the statistic of it. So I think everyone here knows what is mean, standard deviation, minimum value, median value, and max value. Before doing this, for each for India, what I did is, if I work with all the large values, the total number of births, these numbers will be very, very large. The first analysis that I want to do is, if I go through all the 16 years worth of data, how much deviation do I see? Do I see that in Jan, today they were like 12% of the births were happening in Jan in 2016, but now it's like 25%. that will get quantified by in the standard deviation bucket. So the value that you're seeing, before I calculated this, I calculated the percentage value, right? So in this case, I'm creating a new column, which is percentage of births that happen in that month per year. How do I do that? I just take the live births and I divide it by the total number of births that happen in that year, right? So that becomes your percent or PCT column. And all the stats that I'm calculating is on this column: mean, median, mode. You can calculate everything. So if you see this, what are some inferences that you can draw about this data? Let me ask you more targeted question. Do you think that in 16 years, the percentage of births that are happening in January change a lot? Yes or no? If yes, why? If no, why? Just to revise, this is the mean percentage of births that happen in Jan across 16 years. This is the standard deviation. This is the minimum value. This is the maximum value that you will see in 16 years, and this is the median value. So based on these and what we have studied there, so median is quartile 2. This is also called median. This is variance. How much spread is it? So higher variance means lot of spread of the data, or other values are very different. So in this case, based on the mean value and the standard deviation, what do we conclude? Is Jan varying or not varying so much? So the quartile 2 in this case is the median, which is 8.24. So on an average, right, on an average broadly, 8.24% of the births across all the 16 years have been happening in Jan. Okay, this is the average value. I look at the standard deviation, which is square root of the variance. It's a measure of how much spread do I see. What it tells me is that in 16 years, it has only changed maximum by, let's say, 0.25, right? Broadly. It doesn't vary a lot. So if I were to draw, for example, if I were to visualize, and we will do that as well, if this is Jan, if I draw the box plot, it is telling me that this is 8.24, this is 8.24, and then the whiskers, which is, let me draw the box. This is your quantile. This is your quartile 1. This will have some quartile 3. But this box is going to be very, very small because your entire standard deviation is very small. It's only 0.25, right? So maximum, this will be like 0.25 times 2. This will be 0.25 times 2. That's a good question. Yes, yes. That's correct. So when I'm drawing here, I'm visualizing the median because that's the middlemost value. How I'm quantifying the spread, that is through the deviation from the mean. That's correct. In this case, it doesn't matter so much because they're very close enough. But otherwise, your interpretation is correct. Like the standard deviation is attached to the interpretation of the mean. So you would ideally want to say how much does it deviate from the mean. The reason we usually don't do that is because mean can be influenced a lot by very large or very small values. So for example, if I measure the height of this of the people in this room, and let's say one is 5.1, 5.2, 5 feet 2 inches, and so on, 5.3. But if somebody comes as a 10 feet, then this average will become 6 feet. But if I take the median value, it will still be 5.2, 5.3. Yes. You can take the standard deviation because it still tells you the spread. So here standard deviation will still be high because that 110 value is shifting everything apart. So it's going to say that overall spread in the data is still high. Right? And you can see this even if you visualize, right? So for example, if I visualize, then I will have a large bar here and then the other bar here. This is 5 feet, this is 10 feet. There's only one person here, there are 3 people here. So there is a lot of spread because when I calculate the mean, it comes here, 6. But because of this, the spread has increased. So it's still a good measure for the spread in the data. Okay, so what broadly tells us is there is not much variation that's happening across the years, which is what we saw in this heat, in the original heat map as well. You can see that, you know, that reddishness is maintained throughout overall. Okay, now we will do the visualization that we have done so far. So for example, if I run this particular code block, it is just, again, you can ask your AI, how do I draw a box plot of different, at different months, how many percentage of births that are happening. So now this is a box plot. It's simply a visualization of the summary statistics that we calculated here, right? So these are called summary statistics: mean, standard deviation, min, median, max. And based on this, we can draw the box plots. And here also, let me zoom out a bit so that you can see the entire plot. You can see kind of the patterns that we saw earlier also. It summarizes all the 16 years worth of data that we have. We started from 2009 and we went all the way till 25, I think. So here we can see that it's not changing a lot, right? Like it's going from 7.9% to 8%. It's not a huge change. So overall, the pattern that we see in terms of births looks very tight. If you see something like this, you can actually start to think about that. What is the other possibility, right? If what we were observing, if somebody, for example, fudges the data for 5 years, you will start to see huge variations here. Like this whiskers that you're seeing here will go all the way till here. Like sometimes it becomes 10%, sometimes it becomes 6%, or even like 15%. This is essentially telling us that if I want to do predictive modeling, right, your variation ideally should be less, because that's when you can develop very tight models. So that's what this plot is trying to imply, that when I measure the conceptions in a particular month and I look at it across years, there's not much change happening. Then you can do prediction. If it had been changing a lot, or if it was dependent on the year, then prediction becomes hard. If it changes, for example, because we are not having births anymore, we are like any other country where there is the fertility rate is like now 1.5 or something, then this number could have changed, and we would not be able to do prediction in that case. But luckily, in this 15 years, there's not much variation that has happened in the pattern that we are interested in identifying. We can identify the same plot using a ridgeline plot. So I had showed you again this also. It's called a ridge plot. And you can kind of see what is the difference here. It again shows you how much spread exists. The values are the same, but the way to sort of look at this data is slightly different. This overall shows you what does the distribution look like, which a box plot will hide. Okay. We can also draw the same heat maps that you showed. So each data visualization is serving a different purpose. The first visualization, which is box plot, is telling me how much variation do I see across all the years summarized into one figure. The second one also tells me what does the distribution of those look like, how much spread do I have, and what is my individual contribution. This shows you everything all at once. It's like a three-dimensional representation. One dimension being your years, the second one being your months, and each individual value being the value observed during that month. Again, you can see that this is all red, blue, green, and the reddishness starts here. Okay. You are welcome to change a state here. So for example, this is Kerala. So if you have your notebooks open, you can change this state to something else. But before you change, what do you notice here? If the idea of a heat map is clear, what is the difference? Let me zoom out a bit. This is the maximum zoom out that this is for India. Okay. And this is for Kerala. What is the difference overall, if I just focus on this part? Okay, that is one interpretation. Where is the birth peaking? Yeah, there are two peaks, right? There is some peaking happening here, and there is some peak happening here, right? There is a lot more red here, a lot more red here. If I recall and if I show you, for example, let me switch to Bihar. If I switch to Bihar, for example, you can see that it's bluish and it's reddish. Just because of this outlier, the pattern has because again this could be a data entry issue. There are so many births that are recorded in November 2009. Very likely is a data quality issue. That's correct. Yeah. Right. Yeah. So what when I draw this for the India, it's basically taking all the patterns and sort of averaging it, and likely it will be driven by large states, right? Because if I have a large state and if I have higher number of births, those percentage will be the one which will usually be more stable. So it's usually been driven by states which have very similar patterns. So my point was to okay, let me draw Odisha. What do you notice? Right? So there's some stuff happening again in the May, right? It's not clearly dividing between the first half and the second half. You can see there's more, lot more reddishness again here. So in other words, the seasonality, which is essentially when do these cycles repeat, it looks like it could be repeating in like 5 months or 6 months here. It's like May followed by, I think, November is when it peaks. So there is another way to visualize this, right? You have done seasonal composition analysis. You've done STL, right? Professor Sharad Bhartiya covered how to do seasonal decomposition. So you can take a time series data. So what is a time series data? Very simple. It has on the x-axis, it has so on the x-axis we have time, and on y-axis we have some measurement, which could be, in this case, these are births. So when I draw this, it looks like a periodic pattern. This period, when it repeats, so usually if this is 1, this will be 12, this will be 1, this will be 12, like 12 months, 12 months, 12 months. But I think, as we saw in the case of Kerala, it seems the curve is like this. It's repeating every 6 months as compared to this is 6, this is 12, 12, this is 18, this is 24, and so on. They're repeating every 6 months. You can decompose this data. So I think Professor Sharad Bhartiya must have talked about seasonality decomposition analysis, which is a mathematical technique. So I will not go into how fully that is done, but the broad idea is this is your observation signal. I want to break it down into 3 components. Is there a seasonal component? Is there a trend component? What is the trend component? So it can happen that, maybe Bihar is a very young state. So it's very likely that the number of births might be increasing. But right now I'm not interested in that pattern because they're increasing, but that's not of my interest. This is what you see here. This is a trend. So if I take my observation and I look at the trend, it increases. I can extract what is the seasonal part of about it, right? So when I extract the season, you can see that this pattern repeats again and again. Now, let's try to, this was for Bihar. You can repeat this again exercise for Kerala. And you'll see this. What is happening? You can see the 2 bumps, which is that 6-month bump. So every 6 months, things are repeating as compared to 12 months. So there is a peak here, goes down. Within the same year, there's another peak, right? You can also quantify this. This is just to show the same example in a slightly different way. If I summarize this, in Kerala, this is what it looks like. And let me do it for Bihar, just to be consistent and not for UP. Okay, so for Bihar, this is the pattern. Every 6 months, you see a peak. One peak is in May, the other peak is in October. Okay, whereas in the case of Bihar, the peak is in October, November. this month. And this cycle repeats every year. In this case, this cycle repeats every year. So more babies will be born in May, then followed in October. Right? So if you know, if again the cultural practice, I think, idea is correct. Oh, let's do for Jammu and Kashmir, sure. I think it's called Jammu and this one. It dips fully in April, but it's not as prominently different, which is what you saw in the plot here, that there's not much. Sorry, there's not much. Yeah, this one, sorry. So in this plot, Jammu and Kashmir is the last plot because there's not much seasonality here. So actually easiest way to see this is to do the STL analysis here, right? So this is our seasonal decomposition analysis. Let's try to see if I do Jammu and Kashmir. This is not as seasonal, right? Like this is just kind of like a random pattern, because when it is seasonal, it really stands out in terms of this bumps cycle. Whereas in this case, it's slightly random pattern overall. Okay. Any other questions so far? Okay, so we had births, we can reverse it and we can form what's called conceptions. So for example, if I take Tamil Nadu and I plot the overall conceptions with respect to the temperature, then you again see this negative correlation where x-axis is the temperature, y-axis is the percentage of conceptions that are happening, and each dot here is one single month. Okay, so now our goal is to see if we can model this data. Can I predict, for example, that in January 2026 or January 2027, based on these conditions, can I predict the number of births that will happen? How am I going to be able to do that? So my hypothesis is that this is a function of the temperature that we see, right? So if I just look at overall distribution, so the same curve that you plot there, this is showing you the histogram. This is called a histogram, which is for April, how much, sorry, this is quantifying for each month, how much is its variance as compared to its mean. So when you draw Gaussian, there the assumption is that this variance, which is a spread, is constant, or it is the same across all the months. But in this case, you can see that that number is changing a lot. So to model this and to model counts data, we don't use ordinary least square, or you don't use your normal Gaussian prediction. So I think Professor Manibhushan has talked about the linear fit, where he showed the best line fit that you did to the data. We will start with that model, right? So we start with that model. So I'm fitting the model here. So I just take a random example from Arunachal. I take Dibang Valley. I also have data about each districts. This is the conceptions per month. You can see that the fertility rate is going down, so the number of conceptions are going down. But what I care about is the seasonality. So if I try to fit an OLS is a linear model. It's called ordinary least squares. It's basically what it is trying to do is, if I have scatter points like this, it's trying to fit this best fit line, which goes along the line. Now, if I fit that line, which is this green line that you see, the black line is the actual. And if I calculate the prediction interval, which is the confidence that I have that that line is in some sense the truest line that I can fit, you'll see that sometimes those predictions can become negative, which is not possible. Number of conceptions, even if you're trying to predict, can never be negative. That makes absolutely no sense. Right? So the reason this is happening is because when you fit a line, the assumption that you make is these points follow a normal distribution, right? So the point that you're seeing here is assumed to be coming from a distribution which looks like this. However, when you draw, if I plot the distribution of the number of births, it will not appear like a bell-shaped curve. It will appear a curve which would look like this. And this often happens when you're measuring counts, right? So for example, if you have counts of commodities, counts of shipments, counts of patients visiting a hospital, they cannot be modeled using your ordinary least squares. They require, which is that you cannot just do a normal line fit there. You have to think about that these are counts. Can I do a better job at it? So that is done using what's called a negative binomial model, right? So again, we will unfortunately not have time to go into the full details of it, but broadly what the takeaway should be here is, if you see something which is being measured as the function of counts, your usual assumption of a bell-shaped curve will not apply. You should use other counts based models. There are two famous counts based models. One is called the Poisson and the second one is called negative binomial. What is the difference between those? So these are count models. These are models which will use when you have count data, right? And count data by definition is not continuous, it's discrete, because I can have a count of 10, but I cannot have a count of 10.1 or 10.15. So if I have, for example, 10 babies, 5 babies, 4 babies, 3 babies, and so on being conceived, I will model this as a Poisson or a negative binomial distribution. And this you can do using your code. The distinction between these two models is this assumes that the mean, so if I calculate the mean, I can calculate the mean here by averaging 10 plus 5 plus 4 plus 3 plus 2 plus 1, and I can calculate the variance. It assumes, the first model assumes that your mean and variance are equal, which often is actually not the case. So that's why we fit a negative binomial model where that assumption is not true, right? Where it does not assume that the mean and the variance have to be exactly the same value, because often in real life we don't usually come across those scenarios where both of them will be equal. So now I fit a negative binomial model. So I'm fitting again a line. So this is our goal. I'm still fitting a line, but I'm not making an assumption that these points came from a bell curve. I'm making an assumption now that these points came from a distribution which looks like this. So this line will be slightly different. And what it helps me is, it helps me prevent. So the green shadows that you're seeing here is the overall fit that the line is predicting. You can see that it never predicts zero births or negative births. It never ever predicts that there will be negative births or negative conceptions, because it knows that these are counts. So it knows that they have to be greater than or equal to 0. Okay. So I know we are close to 1. I'm just going to end in like 2 minutes. Any questions about this? So just to summarize, what I have done so far is I wanted to model how births are happening as a function, which is a time series. I want to model how do I fit this curve. Why do I care about it? Because if I learn this, I can predict that tomorrow, if the temperature rises, how will the births look like, right? So tomorrow, if the temperature rises, in this is 2027, for example, will the births still look like this, or they will start to rise, or will they start to go down? I can predict this. That's my ultimate goal. So for that, I'm fitting this model. Okay, that's what I'm doing here. Okay, so we will try to fit a model. So you cannot see this model, I will visualize it. But overall, when I fit a model, so let me just do this one part here. So if I fit a model, what I do is I take the entire India's data and I say that I want to learn how does the temperature across different months have an influence on the conceptions. So I'm taking full India data, but I know which state also I'm taking the data from, and that is, so if for example there is Tamil Nadu here, there is Bihar, sorry, I should draw it here. If there is Bihar here, then I'm trying to fit these lines separately, but I'm putting them together, because when I put them together as one, I get information about how much variation do I see in the same month across different states. So for example, if I take January, I know that now I could have fit simple models. I could have gone to each state and fit this line, but I'm not doing that because it will not help me learn what is the effect of temperature. Why? Because the temperature is confounded with month. January will have an average temperature. So there is only one observation for Tamil Nadu for January. But if I do this across India, across different states, for the same month, but for different temperatures, I have the observation in Tamil Nadu and I have the observation in Bihar, for example. That's what this particular model is trying to do. So when I fit this model, I can also ask that tomorrow, so you can assume that this model I'm able to fit. Now, once I fit this model, I can ask that if the temperature drops down by 1 degree Celsius, so if this was your temperature line, for every 1 degree, let's say this is minus 10 and this is minus 9, for every 1 degree drop in temperature, how many conceptions are going to happen? And what that model tells me is for every 1 degree rise, right? For every 1 degree rise in the temperature, I will see 2.1% less consumptions. Yeah. That's right. That's correct. That's correct. Yes. Oh, that's a great question, right? So what this model does not account for is the decline in the fertility rate overall, right? Great question. So we'll not be able to answer the full question here, but what essentially you're asking is at what temperature do you start to see saturation, right? Here I'm not asking questions about the fertility so much. What I'm asking is in terms of the seasonality that I see a relationship between temperature and conceptions. So if I have the same, it is absolute when I fit the model. But once I fit the model, I can do these theoretical questions. I can ask that if I change the temperature by 1 degree, in one state, how much do I see the drop by? So this 2.1% value that I'm seeing, this is overall average of entire states of India. But I can go to each individual state and you will see that this is going to be different. Because we saw, for example, in Kerala, if the temperature rises by one, so let me show that plot. I can break this down by the month level. So if the temperature rises by July and August by 1 degree Celsius, it has the strongest impact, right? These months are also the months where lesser conceptions are happening, by the way, because very few babies are born in April. So if already I have lesser conceptions happening, if the temperature rises there, that has higher impact as compared to in the colder months. So in other words, if colder months become slightly hotter, it doesn't have a huge impact on the total conceptions that will happen, because we are still above, our belief is we are still above that threshold, which is what you're asking, at which the sperm and the egg are, I think, are able to fertilize properly in general, or maybe two people are able to come together in general. But if it happens to be in these warmer months, that heat human body feels much more, and that's why you have fewer conceptions. Does that idea make sense? So it's being very close to being written up fully. We are in the process of submitting. So for that, so basically this idea, so I will just end here because we're already 105 and this is the final plot that I wanted to show you, that what we are calculating right now is a portion of the actual births that happen in India. This is civil registration system. This is the HMIS data, which is the gap there is 2 to 3 million births that are not being captured in the HMIS data, which we should be doing. which we should hopefully close the gap. But overall, the patterns hold up. Just one final thing, and I'll stop here. Is we can use this to do predictions, which is what initially I started my data for. So, for example, if I learn my this is observed, the black one. The dotted one, which you can kind of see here, is the fitted value. This is my training set. Then I learned till 2021, and then I can predict how many births will happen in each month. Either this is for all over India, and you can see that we can match very closely. But for some states, we are not able to do very well, right? So one of the examples is Uttar Pradesh. Here, Rajasthan also, we are able to capture very well. We do this overall very good for India. But there are some states, for example, Tamil Nadu, where we are missing the peaks. We capture the pattern, but we don't capture the absolute numbers. And here in Uttar Pradesh, again, we capture the pattern, but we don't capture the overall numbers. You can see the reason primarily being because there is some increase in fertility that is happening, which we don't explicitly account for example. Okay, so that was my last thing that I wanted to talk about. If you have any questions, I'm happy to answer them. The slides have slightly more different set of things. I'll just show you my. Sure. Self-learning, fair enough. No, so I will do that. Yeah. I see. I know. Yeah, that's what I was wondering, that it might have been shared with you because I was asked to upload it. No, no. No. I mean, and in this campus, usually you will not find people who will try to gatekeep any knowledge or any information. Okay, I'm very sorry to hear that. Yeah, and we are always looking forward to that actually. Yeah. Not like that. First of all, I'm very sorry for your experience. I will pass this feedback to the team. This is my first time actually teaching, because I sit in a different center than the center which is actually organizing it. So all I was told was to upload it, and I believe that that was shared with you. So that's what I did. But I am not going to do any gatekeeping. All these sites are open. If you want, actually, we have been trying to work with government. So one of the ideas there is to be able to use all the data. For example, all the data that you saw here is public. So we are trying to build, for example, very simple things, right? So there were a lot of questions about, I think there are people from tribal ministry also here. So one of the things, for example, we've been trying to understand is if I try to quantify the diversity of India, what does it look like? So this is, for example, the overall distribution of the census data from 2011. Um, and what we wanted to, for example, understand is, why are there certain isolated tribes? What is the overall diversity in terms of the languages that we speak? If I do, for example, if I go to Assam and I look at the overall diversity, what does it look like? So we have been, just showing this as an example of what we've been trying to build. There are other such things there. For example, you can actually overlay this information on how much we spend on the food. So this is, for example, egg, fish, and meat. You can kind of see a pattern here again using a heat map. That if I draw a vertical line here or a diagonal line here, this part of India eats a lot of milk, eats a lot of fish. But if I switch to milk, which is, let me do, yeah, milk. Sorry. Yeah. So the idea behind heat map is you are able to visualize uh, 2 or 3 dimensions of data at once, right? So in a static bar plot, all you see is, okay, this is the category and this is what is happening. In heat map, you have 2 axes, right, which is your x-axis and y-axis, but it allows you to see overall how patterns have evolved or how patterns have changed across geographic boundaries or country or year boundaries, right? So that's why we use a lot of heat map. Yeah, yeah. Yeah, the class is over. Thank you so much. Yeah, thank you, thank you. Yeah. In the last few years, yeah, just because we have been, like, a lot of people have been thinking about what are the right ways to visualize to bring out the contrast, because often when we draw things, the idea has been that, okay, this is what it, oh the, हाँ तो color pattern का I will check. Actually, I don't. Unfortunately, we are told to carry, but I don't carry. 1 second. 1 second. Let's see. But I can give you my number and email if that helps. Yeah. I was earlier a student here. Yeah. I'm a faculty member at. No, so 2009 to 14, I did chemical engineering, and then I went for studies. I did my PhD outside, and then came back in 24. So 10 years outside. No, I'm not a faculty in C Minds. I'm in a different center, which is called Center for Digital Health. So that's where the difference is. Let me see if I have it. I have others cards. Just take my number actually. 79 77 24 29 36.
Saket, I am interacting because right now I am. Could you please repeat?
So yeah, 79 77 Pulkit. Yeah.
7977
24 29 36. 2936. You can give me a call. My name is Saket Chaudhary.
I'm working in rural department right now.
I see.
I'm from Maharashtra.
Oh, wonderful. Okay.
This health sector also is one of the sectors which I'm working.
Oh, wonderful.
It was very insightful that you told about this.
Yeah, Ajay Kumarji. Yeah, yeah, yes.
So one of the problems right now, I'm in Chandrapur. One problem that we are having, our maternal death rate
is higher
vis-a-vis the state average. Also, the neonatal rate is also higher. One theory which is given is that we are adjacent to Gadchiroli. It's around. It takes an hour and a half.
So overall nutrition state.
No, sir. I'll just.
Sure, please, yeah.
And then then this Telangana border is also there. When I talk with my doctors, they give me a concept that people migrate from there for delivery, and that happens here, and that is recorded here. So it's about when we go into that cycle.
But do you not sort of have that data about where are they coming from?
That I can get. That only I wanted to. And the other reason why I want this study is because our infrastructure that we are getting, that is as per the planning that they have done for us, keeping in mind, not this migration aspect. So if you can help me, like,
yeah, that's
other digital things, like other related to health also, if you are working.
Yeah, I'm actually doing. So we are doing exactly the same thing. Again, we are limited by. So this is our neonatal mortality.
You just tell me, like, if you want to do some study.
Yeah.
Because as such, the entire health infrastructure of the district is my responsibility.
Oh, fantastic. Okay, fantastic.
I do have like people working. I'm also IT graduate only.
Oh, wonderful.
I graduated in 2015 in mechanical engineering.
From here?
No, not from here. I'm from IIT BHU.
Oh, wow, fantastic. Wow, wonderful.
So, matlab, if you,
No, I'm
if
pleased,
anything
yeah.
else also you are working.
Yeah, so I have multiple
I'm
things.
staying
Whatever
here tomorrow also.
Okay,
Matlab, if
fine,
you're free, we
fantastic.
can discuss.
Sure, I'm
your-
happy to. What time will you be free?
I am free throughout the day. I'm staying tomorrow because I have a meeting in Sitara.
Ah, Sitara, okay. I see.
Professor Bakul.
I see, Bakul Ram. Yeah.
Time we have another. I am meeting Madhur sir.
I can
also.
meet you for breakfast, whatever,
Yeah.
39.
You just tell me, like, I'm very flexible.
Yeah, yeah, you are in Padam here or?
I'm staying here only, upstairs.
One here. Okay, I will come for breakfast and we can meet for
Yeah,
breakfast.
because
and I can show you what kind of work we are doing.
like talking to you, you brought out a very relevant issue. Like
Right.
for us, it's very relevant when the birth rate is going high. We should be more on our toes,
Right.
taking care of like whether all doctors.
So we have a lot of hypotheses about neonatal mortality.
So you tell me like whatever I learned from. See, as
Yeah,
I
yeah,
told
sure,
you, I'm
sure.
not a health
Sure,
from the health background.
Sure, sure.
So my intention is also at times just to have an inference and
Sure, sure.
take care of that only.
Sure, sure.
Data and all that if is required, I'll coordinate with them. And if you can give me some insights,
Sure, I'm happy to.
particularly related to maternal health, neonatal health, diseases like sickle cell,
Sickle cell, of course,
like
yeah.
then this non-communicable diseases
Right,
which is getting a fad now.
Yeah, yeah. So we do a lot of
So,
stuff on disease burden also. So like we have been again, a lot of us, a lot of
You
our
just
work-
tell me the time
I will do.
tomorrow.
I will message
accordingly.
you and I have your number. I can just save it because I got 3 calls. So
Seven.
this one I have.
Yeah.
Now Google already tells it. So
Yeah,
that's
yeah. I am
IS.
IS Maharashtra cadre. So I want to be associated because I'll be there in Maharashtra only for coming
for
years.
comment, right.
And it's easier for me to
I know.
come and
Geographical location does help.
yeah, yeah. Earlier also many districts did some projects with Sitara,
Right.
but they are carrying on those projects only.
Right.
So I
No.
want
So yeah, I'm happy. And this has been my kind of more close interest. I spend more time doing public health than my other fields. So,
Yeah. To be very honest, I just have a basic idea of public
That's
health.
fine. That's fine.
Because
We're all learning actually.
Being coming from that background,
Of course.
and that is more knowing about the supplies,
Yeah.
medicines are there or not.
Right.
Nitty-gritties I'm not aware. If you tell me some insight like what kind of data you want, that I can ask.
Sure.
Because you might be having more awareness to what thing is.
Yes, I do. Yeah. We have. I will show you. Like, I'll come with presentation and I'll maybe give you a write up of what kind of things we can do.
Right now I'm based in Chandrapur. Chandrapur is a kind of tribal district.
Yes,
Also, we have a good significant tribal population.
Correct.
In percentage terms, it's not. It's only around 14%.
Okay.
15%.
Right.
But the population is high, and there are PVTGs also there.
Right.
Like the column group and all that.
Right.
So we have some specific issues for
Going
them
with
also.
the tribal population.
Yeah. And then apart from this, it's a kind of semi-urban, rural also. Some industries are also there. So it's quite a complex thing which is studied.
Sure.
And health infrastructure is severely needs to be taken
care of. No, totally. And I think the next few years will be health is what we should be focusing on.
And especially when what we try to go and convince that our